So what is the problem? You have a graph, you get a source S, and you want to compute all these shortest path distances from S to V. So you fix S and you want it for all V, right? So that's why it's called a single source shortest path. And if the graph is unweighted, meaning that you're just counting the number of edges on a path, then this is just breadth first. You can do this with breadth first search. But in general, edges may have weights. The weights are usually denoted by W. So W is like a distance or a weight or a time between U and V. So every edge has a weight, which is often stored in the adjacency list. And so the weighted length of a path is, of course, just the sum of weights. And so this is the problem now. So where you want to sort of compute the shortest path. You want to compute all pair shortest paths. Now you might wonder, often in many applications, I give you a source and a destination. I just want the path between that, right? Like when you do Google Maps. Interestingly enough, we don't know how to do it much better. I mean, okay, I shouldn't say that in general, but there are certain heuristics you can use, but in general, most of the algorithms that compute the shortest path from a source to a destination often end up computing lots of shortest paths because we don't know exactly how you can hone in onto one of them. So the heart of this algorithm that I described is actually the heart of doing it even when you want to do it for a single source and a single destination. Does that make sense? So somehow, single source and single destination doesn't seem to make life that much easier in general. Okay? And specifically in Google and actually in Yahoo before that, when a lot of the map software was being built, there was a lot of effort into speeding up single source shortest paths, right? And I still remember, I know the guys who were, at some point, they put, now maybe it's not a big deal for you because you're used to this feature where you can put a destination, you can put like a breakpoint in the middle and it will actually route to that midpoint and then take you, right? You can, and then it came to the extent where you could even like click on a point, you could drag it around and it would sort of tell you what the shortest paths are. That was really hard algorithmically. Like it was a big deal when people figured that out. Of course, not for the rest of the world, but I'd spoken to some of the people in that research division and they had put in a lot of effort into how to figure that out so quickly so that you can get real-time answers for these things. And you'll see because a heart of all of these things is Dijkstra's algorithm, which is not very good for like real-time changes of like a midpoint. Okay, so in general, weights can be negative, right? And we discussed this. So when the weights are negative, for example, if you have this cycle here of negative weight, then shortest path distances aren't defined, meaning that they can become minus infinity. In which case, you don't even have the notion of a shortest path. You might say, no, I want the shortest path which doesn't repeat a vertex, but that problem is actually hard to solve. It's known to be NP hard. Like the moment you start imposing constraints of that form, the problem suddenly becomes hard. So, okay, which is a big surprise. So the thing is that when we start talking about graph algorithms, things go quickly from being like linear time or breadth first search to actually being NP hard, where we don't even know how to do them efficiently. Okay, so now as we discussed, the way that the shortest path algorithms that I'm going to talk about work are again sort of analogous to BFS. They maintain these two arrays. So one is the estimate array, and one is the predecessor array. So the predecessor is just like predecessor in breadth first search, right? It's basically like the parent in the shortest path tree. The estimate is going to maintain an estimate of the true distance, and that estimate is going to keep reducing over time. Like that's how these algorithms work. It's like they successively improve on the estimate until at some point the estimates will converge to the true answer. Okay? So what are the invariants that are maintained? So this invariant means that at every stage of the algorithm, these statements will always be true, and they're both sort of coupled. It's all about the tree. So what it says is, if you ignore the mathematical notation, it says it's maintaining a particular tree, right? And the estimate is simply the distance on the tree from S, right? S is the root. So it's maintaining this tree. Now the graph is a bigger graph, But it's just like BFS, it's maintaining this tree, and the estimate is simply the path on the length of the path on the tree. Okay? Now, if you note something, this is not entirely, it's not obvious to prove, but it's not very hard to prove either, is that the nice thing about a tree is that from any vertex to the root, there's this one unique shortest path, right? You just go to your parent, so on and so forth. So routing on a tree is really easy. But routing on a graph is really hard because there are so many options, right? So if you think about like the internet, how does it work? I mean, if you think about it, it's you just go to google.com or whatever website, or you go to YouTube and you say, I want this video, and then the video streams immediately. But obviously what's happening is that content is sitting on some server somewhere, which has to send it somewhere, which has to send it somewhere, which has to send it somewhere, which sends it to your internet service provider, who's then going to route that all the way to you, right? And a lot of this is also done with shortest path routing, which are all maintained. I don't know if you recall, there was this one incident where, so it was a few years ago. So I think it was in Pakistan that essentially there was some video on YouTube that they thought was offensive or blasphemous. And so what the ISPs in Pakistan did was they basically shut down YouTube, right? So what that means is those internet service providers will stop routing any traffic from YouTube, right? And then YouTube went down for like a third of the world. So why? It's because in that shortest path tree in that tree that was built at that time, some of these nodes were essentially Pakistan ISPs. And so anybody below who had to route couldn't go because they were getting stuck there. So that's one of the problems with trees, trees are also fragile to route. Like one node breaks down, and then all of these cannot get anywhere, right? So there's this interesting thing about the simplicity of the tree, but also the fragility of the tree, which, I don't know. So that's why like research and problems in shortest paths are still ongoing, because there are so many different aspects to understanding shortest paths. Okay, so having said that, let's go back to this algorithm, or not this algorithm, but rather this setup here. So you have estimates, and you have these paths, and the predecessors. Okay, so before I even tell you an algorithm, I'm just going to tell you generically how are we going to initialize these. This is sort of obvious, right? So the initialization is pretty easy. It just says that the estimate for S is going to be 0, and the estimate for V is going to be infinity for all vertices that are not in S. And then for all vertices, the predecessor of that vertex is null. Right? This is like the obvious way you'd initialize. You'd say for every vertex other than the source, I don't know what the shortest path is, I'm going to assume it's infinity. So that way I maintain the invariant. And there are no predecessors. Right? So, fairly clear? Okay. This is actually the ideal class size, a little bit more than this to teach algorithms. Like maybe about 40 students. So, so please, stop and ask me questions. So, now I'm going to define a particular operation. Okay? So I'm going to write this out. I'm going to define an operation that is safe. So what does safe mean in this context? It means that the invariance will be maintained. So I'm going to define a particular operation that is going to change the tree And it's going to change all these estimates. And what I'm guaranteeing you is that the invariants are always going to be maintained. So before even telling you what this operation, the nice thing about this is you can do any sequence of these operations and you'll never sort of make a mistake. You'll always be maintaining these. Your estimate is always going to be at least the true distance, and you'll have a path, yeah? Which is the output of the BFS. In this case, it's not BFS, it's this other algorithm, but yes. That we haven't defined yet. But in BFS, this is, in BFS, the estimate would simply be the number of edges on the path to the root. Does that make sense? You wait for the algorithm and you'll see. But the thing is that to get to the algorithm, I have to define a bunch of things. So I'm going to define this operation that is called relax. And, well, the reason why it's called relax is not because it has anything to do with being stressed and being relaxed, but because this is related to something called linear constraint relaxations. But anyway, okay. So relax is going to take, really it's going to take an edge as an argument. So technically, what it does is it takes a pointer to the edge UV. So the pointer, meaning the pointer in the adjacency list, right? This edge is sitting somewhere in your adjacency list, right? And I'm going to give a pointer to wherever that edge lives in the adjacency list. Okay? Clear? All right. Okay, so what is this procedure? It's actually pretty straightforward. It just says that if the estimate for V is strictly greater than the estimate for U plus the weight of the edge UV. Okay, so suppose this happens, what does this mean? Tell me, what does this mean? It means something. Suppose the current estimate that you have for V is greater than the estimate that you have for U plus the weight of UV. Then what? Something is going to happen here. Yeah? Then it says that you can actually improve your estimate for V. Right? Because what it's saying is that instead of whatever path that you had to V in the tree, you're better off going to U and then going U to V. Right? That's what it's saying, right? So you got an improvement that is safe. What does safe really mean here? It says that for any estimate that you actually have a path that has that distance. That's what safe means, right? The path on the tree. So if this is the case, then I'm going to set the predecessor of V to be U, and I'm going to set the estimate of V to be the estimate of U plus WUV. Running out of ink? No. Okay. Right? Yes? So it's all, remember, it's all single source shortest path. S is fixed. The source is fixed. S is fixed, exactly. There are actually not three, well, yeah, S, U, and V. So in all of this, the reason that I'm not carrying S around is because I'm only giving you the shortest paths from S. There is also this question of what's called all pair shortest path, which is compute every pair of shortest, like all shortest path distances. That's another problem, which you could solve by just doing a for loop on S with this, but there are other ways of doing it. Okay, so this is this procedure relax. So what this is saying is simply that, look, here's your tree that you have right now. And so here's a vertex U, or I'll say this is V. So you have some path on the tree that goes to V. And you have some path that goes to U. What you have discovered is that instead of going down the tree path to V, if you went down to U and then took this edge uv, it's actually shorter, right? So what you do in the tree is you modify it. You say, okay, now make the predecessor of vu, which means you're effectively removing that edge from the tree, right? V is switching its parent, but it's still going to be a tree. Note that what this means is that for every vertex that was using V as part of its shortest path, its path has also changed. Does that make sense? So suppose you had some vertex X here. Its path before was going through V. It's still going to go through V, but now it's going to go to V, then sort of go to U, so on and so forth. Or I should say, this is a direct, it's good, it's useful to think of this as a directed graph, right? So all these edges are directed this way. So think of it that the path from S to X before was taking this edge that I've shaded out, and now it's going to take this edge UV. So this one edge change has changed many shortest paths. Is that clear? So the question I have for you is, how long does relax take? I mean, we can use post-its, we can do whatever, but given, is it basically just O of 1? Is it actually O of the degree of V's, right? This is the degree. Either plus or minus, whatever is appropriate. Well, no, it's, or is it like theta then? So how long does it take to perform this operation relax?
Or until you can't do any more?
Just to do one, just one relax operation. All you have to do is one relax operation. Does the question make sense? Right? You just want to do this operation, and you have access to a pointer UV. You have access to a pointer. Yeah?
Is the ESP, is that value stored in the node, or do you have to calculate it?
It's stored as an array.
Okay.
Right? These are stored as arrays. Right? So nothing is, so just to be clear, like the adjacency list doesn't store any of these things. I mean, you could store it additionally if you want, but you don't need to. So it's stored as an array. So what is the answer? Does everyone see? Yeah? Okay, so yeah, most of you see that the answer is just, it's just O of 1, right? Because you're just accessing 4 numbers here, or 4 quantities in memory. You're accessing estimate of V, estimate of U, the weight, and the predecessor, and you have access to all of these in constant time, because the weight you have access to because you have a pointer to the edge. Is that clear? You have access to the weight because you have a pointer to the edge. Okay, so that's what it is. That's how long relax takes. So a single source shortest path and SSSP algorithm is simply a sequence of relax operations. That's it. It's just going to be a sequence of these operations. And the whole game is now to choose the sequence. So the question you can ask is, okay, so what is the right sequence? Is that clear? So I'm just going to do a sequence of these operations one after the other in some order, and then I'm going to be done. So how many of you have heard of Dijkstras Algorithm? Probably somewhat more common. How many of you have heard Bellman Ford? Okay, so just you. So Bellman Ford is surprisingly less common, but a much easier algorithm. So I'm going to tell you the Bellman Ford algorithm, because it's going to be, at this point, it's going to be 1, 2, basically about 3 lines of code. So, and if I'm not mistaken, the Bellman Ford algorithm was probably one of the earliest shortest path algorithms, right? This is probably maybe about 70 years old or something. This is like in the 50s and 60s where people were thinking about these questions. So remember, n is the number of vertices, m is the number of edges, s is the source vertex. So we're doing single source shortest paths. So first, I'm just going to initialize the predecessor and the estimate arrays. Then what I do is quite simply from I going from 0 to n minus 1, right? So I'm just saying n times for every edge uv, I call the relax operation uv. And that's it. That's the algorithm. So all I'm doing here is, in step 2a, I'm just doing a traversal of the adjacency lists. For every edge that I see, I just call relax. I do this n times. Right? Doesn't get simpler than that as an algorithm, right? Relax is really easy to write. And all you're doing is just calling relax on, you're just going one pass over the entire graph, calling relax on each edge, then doing it again and again and again. Do it n times. Right? The I isn't even that important. It's just saying do it n times. Make sense? It's probably not clear why this works. Right? That, yeah? That's it. So you do this for every vertex, and then you do the whole thing n times. Okay. So first question is, what is the running time? Is it essentially, is it going to be theta of m? Is it theta of m plus n? Or theta of m times n? Let's just assume, I'm just going to assume that m is always at least n, right? Just to keep life simple. Because essentially what you can do is technically you would do BFS, you'd find your connected components and you run it on each connected component. That's usually how it works. And when a graph is connected, then the number of edges is at least the number of vertices, or m. It's at least n over 2. But just assume this for now. Keep life easy. What is the running time? Yeah, does everyone see why the running time is? No, it's actually, it is m times n. It's m times n. Yeah. Why? Yeah? It's just nested for loops, right? So this outer for loop is just going to multiply whatever the running time is by n. This outer for loop here, it's just going to multiply the time, right? So this step runs clearly in O of n, which is like O of m, because I'm saying n is at least m. This entire process is just traversing all adjacency lists once. Right? It's just traversing the entire adjacency list once. And so this is like O of m plus n, as we said, but I said m is at least n, right? So this is just O of m. And this is repeating it n times, so it's m times n. This is what would be called quadratic time. Right? So it's theta mn running time. It actually works even with negative weights. So that's confusing. We'll come back to that. It works no matter what the weights are. Even, it turns out Bellman Ford can find negative weight cycles. Meaning that if you have the situation where you have something like this, and I'd say find such a cycle in your graph, Bellman Ford will actually discover it. It's not obvious, but I'm going to leave that as, it's an exercise, it's a challenging exercise. I put exercise star because you have to think about it carefully. But if you use the Bellman Ford algorithm just as is, you can actually even discover negative weight cycles. You might say, why would anyone want to find a negative weight cycle? So I'll give you an example, but do you know what arbitrage is in a financial market? Okay, so what is arbitrage? Arbitrage says, take $1, convert it to pounds. You'll get some number of pounds. Maybe you'll get like 0.85 pounds. Then you take a pound, you take that, convert it to euros, okay? Then take the euros, convert it to maybe a real. Take that, convert it back to $1, okay? What if you ended up with more than $1 at the end of this process? So you start with $1, and you just do these commodity transfers. You end up with more than $1, right? Could that happen? Sure it could, because exchange rates between countries are decided through some mechanism. Pretty interesting, right? So then you just start making money, right? You would just take $1 and you would keep doing these transactions over and over and over again, and you'll keep increasing money. How do you find that? You can actually convert it to a Bellman Ford. You can actually create weights between commodities that depend on the exchange rate. You have to think of it. It's, again, not that obvious. But you can run the Bellman Ford algorithm to find arbitrage. Yeah?
Can I make a career out of this, or did they put up?
It's called Wall Street. Yes. So what happens in reality is, suppose people discover arbitrage, then they will continue to do that process until what happens is that when arbitrage is discovered, then exchange rates will start changing to get rid of the arbitrage, right? So that's how exchange rates start modifying, because if everybody starts doing a transaction, then the market's correct. But there is a short window in which you can make money. Have any of you heard of what's called high-frequency trading? High-frequency trading is about doing lots of transactions really quickly to exploit arbitrage. To the extent that, I don't know if you know of this, so the thing is that the more transactions you make, the more the market discovers that there's a problem and corrects. So you want to do it really, really quickly so that people don't have time to react. To increase the frequency of trading, people discovered a bottleneck is the speed of light, because to find out about prices, it has to be sent over the internet, and that's the speed of light. So San Francisco has a disadvantage because all the prices are coming from New York, so people move their exchanges to Chicago because it's closer, and they even try to go closer and closer. So there's actually benefit of being closer with respect to the speed of light, because you gain that much. So anyway, but some of it is related to arbitrage. And the way you discover arbitrage, one way to discover it is to set up a graph problem and then start running Bellman Ford on it. Okay, so yeah, so this stuff, there's real money to be made here. Okay, but the thing that you're probably wondering, if you look at Bellman Ford, is why does this thing work, right? What is it about doing the relax operation n times? What's curious here is you could change this by switching these two lines, right? You could say for every edge, run the relax operation n times on that edge. That doesn't buy you anything, because once you run the relax operation once, if you do it again, it doesn't change anything. Does that make sense? Suppose you run the relax operation once. Well, then you've already reset predecessor and the estimate. So if you do it again, you're not going to get anything at that point. But somehow if you do a bunch of other relax operations and come back to the edge, then you gain. Okay, so the argument for this is actually it's very clever. Okay, so let's let's look at a particular source S and a destination V. And let's say this is the shortest path. In reality, this is the shortest path. And so I'm going to refer to this as the shortest path as U1, U2, U3, going all the way up to UK minus 1. V is going to be UK, and S is U0. Suppose this was the shortest path. Okay, suppose I told you this was the shortest path. I even showed you the shortest path. What is the sequence of relax operations you should do so that your estimate is going to be the distance? Tell me, is this question clear? So what is the sequence of relax operations you should do so that the estimate of V is actually going to be the distance of V? Does the question make sense? So I know that you know. So I've told you the answer. But what I want you to do is to fit that into the relaxed paradigm. Does that make sense? I want you, so you know what the shortest path is, because let's say I give you the graph and I mark it out to you, say this is the shortest path. But what I would like you to do is a sequence of relax operations so that the estimate is equal to the distance. So I'm just going to write this question down. What is a sequence of relax operations to do so that the estimate of V becomes equal to the distance, the true shortest path distance. What is a sequence? So there are obviously, this is inside some bigger graph. There's some big graph and there's this path here, and I marked out the path. I just want you to do a sequence of relax operations so that the estimate of V becomes equal to the distance, and I'm showing you what these are. And if you think about every time you do a relax operation, remember, you can add a potential edge to the shortest path tree. Where would you start? Like, suppose I said, do a bunch of relax operations. I'm telling you what the shortest path is. Sorry? Okay, so give me the first relax operation, right? What would the so on and so forth, right? Suppose you call the relax operation here. Then at that point, the predecessor of U1 is going to become S. And then you call it to U1, U2, the predecessor of U2 is going to become U1, right, by this. Because initially all of these things are infinity. And if you call it one by one, you're going to end up with exactly the right shortest path. Of course, this is kind of, it seems like nonsense, because I told you what the shortest path is, so obviously you know what the sequence is. But remarkably, you can use this to prove Bellman Ford works. So let me write this down, and hopefully this will be clear. Suppose we call relax of U0, U1, then relax of U1, U2, relax U2, U3, finally relax of UK minus 1, UK. Like in this order. You call this in this order. Yeah? I'm not writing it out formally, but yeah, you could do it inductively. But in this case, you don't even yeah, okay. Formally, you would write it by induction. Yeah. Yes.
So is the point that because we don't actually know what the viewpoints are, if we run it on each of the points n times, every one of those times you will at least be running it on the one after the one you just did?
Essentially, that's sort of the argument. Yeah. So the idea is, so let me write something and then I'll, yeah. So, but is this clear? Is this clear? If you could magically run relax in exactly the right order, you'd be fine. right? Yeah, you only need like k times, yeah, right? If you could magically run the relax operation in that order, you would know you would get the shortest path from S to V. Although it seems like you needed to know what it was. But now I'm going to argue that even if you don't know what it was, this well, not this one, but rather this procedure is effectively going to call it in that order with a bunch of extra operations in between. But extra operations are safe. It doesn't harm you in any way because it maintains the invariant. So what this is saying is, if we call it in this order, then est of v is going to be equal to the dist of uv, and also for all ui, the predecessor of ui will become ui minus 1, right? Because it's essentially just going to... Now suppose instead of doing this, suppose you did the following. Suppose we call relax of u0, u1 and other relax operations here. So there are a bunch of relax calls that you do, then you do some other relax. Like I don't care what you do over there, and then you call u1, u2, and then you do a bunch of others, and then you do relax u2, u3, so on and so forth, until at some point you're going to do relax of uk minus 1 uk, and you did a bunch of others. Does this make sense? This would also work. This also works because relax is safe. It maintains the invariance. Right? So as long as you can call it in this order, even with other relax operations in between, it still works. And then observe that this procedure does that. Because in the first, when I is equal to 0, it's going to at some point call relax on u0, u1. When I is equal to 1, it's going to at some point call relax u1, u2, so on and so forth. Pretty clever, huh? And so it gives you all shortest paths from S, because this argument, so the formal proof of this requires an induction, which I'm not going to write. But you could, if you're familiar with mathematical induction, you could probably write the proof from this. Like this is sort of this is the insight. It's very smart. Yeah?
Does the tree that this produces, does that contain shortest path distances from all points
to S.
or to S?
From S to everyone.
From S to everyone?
Yeah. And now you can say, what was it about S that actually appears in all of this? It's just that you initialized S to 0. The only thing where S appears. So it's just about who initially started at 0. And that information essentially propagates to give shortest paths. Okay? Because the relax operation is sort of tailored to 0 because the predecessors are with respect to 0. Everything, there's 0, so I'm sorry, the only place that S appears is in the initialization. Like when you initialize, remember the initialization says the distance from S to itself is 0 and everybody else is infinity. If you really think a little bit about how this algorithm works, what happens is, like initially, the distance of S to itself is 0 and everybody else is infinity. And then what it's going to do is it's going to call relax everywhere. But when it calls relax on this edge, nothing happens because the distances between both of those are infinity. But if you look at these edges, there's going to be an improvement. So it's going to get some information about these. Then the next one, it's going to get some information from these edges. So in some sense, the information propagates sort of like BFS, but it's more sophisticated than, well, I shouldn't say sophisticated. It's more complex than that. But essentially, that's the idea. So it all depends on, you said, I'm going to start the distance of S to itself as 0, and so that kind of effectively gets the distances in the end. Yeah?
So you want to kind of go through in a breadth-first kind of manner, then you can reduce the running time.
And that's called Dijkstra's algorithm. Essentially, what Dijkstra does over Bellman Ford is says, well, if you kind of did things in a better ordering, you could cut down the running time because you're wasting a lot of time calling relax operations on these edges out there. So to cut down on that, you essentially do something like what BFS does, which is maintains a queue. And then you put the edges into a queue. But you have to do it carefully so that you get the right order. That's basically, that's what Dijkstra does. Except, okay, so, good. So, you know, I don't expect you to know the proof for Bellman Ford necessarily, but I think it's nice to see. It's like a very cute argument that all you have to do is run this n times. And if I'm not mistaken, I think both Bellman and Ford sort of had this independently, and then they came together. Okay? So, is this argument clear? So just like if you think about this whole iteration, this is be like I is equal to 0. Then this happens somewhere when I is equal to 1. This happens somewhere when I is equal to 2, so on and so forth. Indeed, what this tells you is something better. It says even after k iterations, where k is the length of the shortest path, you're done. Like you don't even have to go up to n, but you don't know what k is, right? Maybe the shortest path actually goes n edges. And that's why you need that many iterations. Technically, I think it's n minus 1. But anyway. Okay. So, is that clear? It's worth maybe showing you a small example of something where Bellman Ford, like, kind of just to see how it goes. So suppose you had a graph that looks like this. S. Maybe this also answers why you could say, oh, why don't you do it in a breadth first manner? I'll show you an example where the breadth first crawl actually does not get the right answer. Right? So, and then you'll see why you have to kind of do a Bellman Ford style argument. Okay, so let me see if. So suppose this was what your graph was, or this was the portion between S and V. Now, in terms of breadth first search, this is the shortest path, right? But I could obviously put weights so that this is a longer path than that. And you'll see that when you do those weights, you have to think a little bit beyond just breadth first order. So a simple argument would be, suppose the weights was 1 in 100, and these weights were 1, right? So if you think about what Bellman Ford is going to do, is initially, of course, everything is at infinity. Then after one iteration of Bellman Ford, by one iteration I mean when I do relax on all the edges, I get this one correct and I get this one correct, right? And so the tree is now going to look like, I'm going to just refer to this U1, U2, U3. I go from S, I have X, and then I have U1. Now when I do the second iteration, the distance from S to V was initially infinity, and then it becomes 101. So then it's going to go S, X, V, U1, U2. Right? Now note that this is incorrect because SXV is not the shortest path. But it's not incorrect with respect to the invariant. The invariant is still true. It says, I have a path whose weight is 101, and this is what it looks like. Eventually, now note that as Bellman Ford is calling the update operation, the relax operation on that doesn't change anything. The only time it changes is when all the information propagates to U3. Then when it calls it on that edge, that's when things are going to get corrected. Does that make sense? Right? So it's going to take time for that, and that's why you have to call it on all edges. Or at least you don't know what else to do. Just BFS order doesn't work. Because if you committed to the BFS order, you'd say, oh, look, BFS found it, I'm done now. But you don't know is that maybe there is a longer path in terms of edges, but it's shorter with respect to weights. Does that make sense? And so then you can, it's actually worthwhile to do this example. And then you'll see that, so at this point you've got this correct. This I put a square because you have it, but it's not correct. You do one more iteration, then from here you'll get to U3. And then you do the final iteration. Now this edge is going to get considered. So it's going to say, hey, I could go 1, 1, 1, and then do 1, instead of going 1 and 101. And at that point, it's going to stick this edge in, and the relax operation is going to remove that. And you end up with your shortest paths. Is that clear? Sort of? Kind of? Yeah? Okay, let's take a break for a couple minutes, and then I'll tell you about Dijkstra's algorithm when we finish. Oh, for the homework, you have to use BFS because it's unweighted. Right? There are no weights on the edges. You couldn't afford to do Bellman Ford on it. It's huge, the graph. You could probably do Dijkstra. It's not that, yeah, but no, you have to do BFS because there are no weights on the edges. You only do Dijkstra or Bellman Ford if you have weights. And actually, you only use Bellman Ford over Dijkstra if you have negative weights. So I'll summarize this shortly. Okay. All right, so we have maybe about half an hour left. Excuse me. So let me continue. Let me show you Dijkstra's algorithm. I should have said something about Bellman Ford, which I did was sort of incorrect. So okay, so just to show you how this tree evolves, right? So let me move it in this direction. So it was SXU. Then you get SXU1. So from X you get V, and from U1 you get U2. Then when you do the next operation, you go S, X, V, U1, U2. Now, okay, so no, this is correct. Okay, sorry. Yeah, no, that's fine. So you get U3, and then finally it changes, and then from here you'll get to S, X. I'm sorry, S, X, U1, U2, U3, and V. Right. So there's that at final point. There's that switch. This edge basically moves. Okay. So that is Bellman Ford. So what about Dijkstra's algorithm? So Dijkstra's algorithm assumes that all weights are non-negative. Okay, so just to be clear, when weights are negative, shortest paths can still be defined. When there's a negative weight cycle, then shortest paths cannot be defined. So there's sort of three scenarios, right? One is all weights are positive or non-negative, or actually there are four. So the simplest one is all weights are 1. That's BFS. Then all weights are non-negative, meaning that you never have something whose weight is negative, right? That's the next situation. Third situation is there are some weights that are negative, but there is no negative weight cycle. And then there's a fourth situation where there's a negative weight cycle, in which case shortest paths are not defined. For each of these different scenarios, typically you have different algorithms that you come up with. So I'll summarize all of this at the end in one slide. So let's assume all weights are non-negative. Now if you think about how we did Bellman Ford, or even BFS or any algorithm, you start with S, and there's some portion, let's say that here, shortest paths are known. So what this means is in this shaded region, you have already discovered shortest paths correctly, suppose at some point. Just as we were doing Bellman Ford, there was like this region over here where we knew all the shortest paths, right? And then you kind of keep going. Now, it kind of makes sense that if you're outside this region, there's no point calling relax. No point calling relax on that edge. That seems like it's useless because you have no information anyway. You should only call relax on these edges. Right, these are the ones that are important. I could direct this. These are called the frontier. So this is like, or not the edges, but rather these vertices. The vertices that you reach just by going outside the shaded region. The shaded region is where you know shortest paths. Like suppose at some point the algorithm has figured out like, hey, here, these are the shortest paths, I know they're correct. Then it only needs to look at the frontier, right? And that's how we're going to save effort. Now you might say, how do you know that the shortest paths in the shaded region are correct? And this is where the fact that the weights are non-negative are going to help us. Okay, so so let me draw this picture sort of as follows. So this is S. This is the shaded region. I'm going to call the shaded region capital S. Okay? And so you have all these edges that are coming out from here. Lots of edges that are coming out from each of these regions. So let's look at a V and a V prime here. Now note that inside the S, the estimate and the distance are the same, right? In here, so for V, the estimate of V is equal to the distance of V. This is a thought experiment. I'm just sort of thinking aloud about how I'm going to construct the algorithm. I'm just saying that inside the shaded region, the estimates and the distances they're the same. But it's outside the shaded region that I don't know what's going on. And I'm trying to figure out what is the next relax operation to call. Okay? So suppose, so this is like for all V in capital S, this is true. Suppose I find an edge, V prime. So V is in S, V prime is not in S, V is outside. So this is edge crossing the boundary such that the distance to V, so that's from S to V, plus the weight of V prime is minimized. So suppose I find such an edge. Right? Does this make sense? So I'm going to try to find an edge such that the distance from S to V plus the weight of that edge is minimized. And I do this over all of these edges that are crossing the boundary. Does that make sense? Okay. What I'm now claiming is that that's a shortest path. Okay, why? Right? So I'm claiming that the shortest path to V prime is through V. Yeah.
So is the claim that the node that connects to V prime that will create a shortest path already exists in S?
Already exists in S, exactly.
And because we have S, we just have to find which of the nodes in S are the ones that V prime can connect to.
Right. So, but I'm sort of turning this on my head. Instead of looking at it with respect to what is the shortest path to V prime, I'm trying to think differently. I'm saying, look, for everything in S, I have the shortest path information. So I have the shortest path tree. And I'm trying to extend that tree by a single edge. I'm trying to discover one edge which is guaranteed to be in the shortest path tree. And I say that this edge is guaranteed to be in the shortest path tree. Yeah?
Couldn't it be that V prime could be reached from some other place
Good.
that you haven't looked at yet?
Okay, good. So, yes. So that's like, now okay, so you're saying, so for V prime, maybe the true shortest path is something else.
Right.
Okay. Now that shortest path is going to come through S and exit at S at some point because little s is inside capital S. Okay, so let's just say that, so suppose the true shortest path went something like this. It went to some x, and then from x, it went to x prime, and then it went from x prime to v. Maybe it goes in, maybe it goes out, I don't know what it does. Now, I claim that if you look at all of the things written here, you should be able to conclude that that cannot be the shortest path. Why? Okay, so does this argument make sense? So, sorry, let me just say what I have to say, and then, so what I did was, I'm assuming that in the shaded region, you know the shortest paths. Okay, I have a shortest path free. So I just guarantee that to you. So
That includes paths that go out and come back in.
I'm just saying that within the shaded region, I have the true shortest path to every vertex in the shaded region.
But it will not change even if you finish.
Even if you go out and come in, let's just say that for each of those, I'm giving you a shortest path tree. Or if you prefer to think of it, you could say, as you think of it, I give you the shortest path tree that is in S and it only has edges in S. Okay? So this is like the region where you know your answers are correct. And initially, if you think of it, you always know such a region because the vertex S by itself is correct. Like you know the shortest path from S to itself. So you always have that region to start off with. Okay, now, what I'm saying is, I'm going to find an edge V prime, where V is in capital S, V prime is not in capital S. So there are a bunch of edges that are crossing the set. Suppose I went through each of those edges one by one. For each edge V prime, I can compute this quantity. What is the distance to V? Because I know that distance. I have it already, plus the weight of that edge. So I do this over all these edges. And I claim that V prime, I'm just claiming that V prime is in the shortest path tree. Now, the argument for that, following what was suggested, is, well, let's prove it by contradiction, right? Let's say, suppose actually this was not the shortest path. There was some other path that goes to x, leaves the set, because it has to leave the set at some point. So it goes from x to x prime, and then it goes from x prime to v. And from there, it might go in, it might go out, you don't know what it does. But I'm saying that that cannot be the shortest path. And you need to use the fact that the weights are non-negative. Yeah. I'm sorry, say that again?
It would already be in S.
Why? I mean, but maybe maybe there's some other path here. You have to use the fact that I've chose this special edge.
It's something the way that S grows. It's the way that...
At this point, like S is, just assume, no, it's not about the growth. It's like S is just some fixed set. I just told you some region, I gave you all the shortest paths, and I said, here are the shortest paths. Yeah. And, yes? Okay, almost, yes. Why? Okay, I'm almost. So you're getting there. So okay, tell me something. What can you say about this path? There's a path that goes from S to X, and then x prime. Like look at what's in the box. Yeah? It has to be longer than this path, because I chose v prime to minimize that. So if going from S to X to X prime were shorter, well then this is invalidated.
So just by definition.
By definition, by definition, going from S to V and V prime is shorter than going from S to X and then X prime. And because the weights are non-negative, if I'm going to go from X prime to V prime, it's only going to add to my path length. Remember, if weights are negative, this argument breaks down. What if this had like minus infinity edge in it? Or this had a really big, like minus a million? Then this argument breaks down. But what this is saying is, if the way of exiting your set was longer, then there is no way that that is going to lead to a shorter path. So it's like you have a set and you're looking at what is the quickest way to exit my set. And so it's kind of like, this is called a greedy algorithm, because you just look at what is your current best decision and you take that. And it turns out that that works in the end. Yeah?
What if this W V prime is like super big?
Where's W?
Like
Oh, the weight. Sorry, yeah.
V prime.
Is super big.
Super big.
But it is still the minimum when you account for going from S to V. This could be huge, and this could be tiny. But if this is tiny, that means S to X must have been huge, because you chose the one that minimizes that entire thing. Does that make sense? So if this was really large, and this was large, then there's no way that this could have been minimized, that this was the minimum. Sort of, kind of? You have your hand up? Huh? I mean, it's pretty much, once you get this, then Dijkstra is clear. Why Dijkstra? Yes?
I guess just to make sure,
Yeah.
the reason why it's the shortest is because we are including the edge weight inside the shortest path. Okay, that makes
And including not just the edge weight and the distance. We're including both of these.
and they have to be equal to each other. The distance x plus the weight of x to x prime has to be equal to the distance v plus the weight
Or it has to be at least. This has to be at least that.
at least. Okay, got it.
It has to be at least that, right? It's just saying that this is going to be at least that, because you chose this to be the minimum. Like, this is by design. It's like saying that you're starting with your set where you know shortest paths, and you're choosing the quickest way to exit from that set. So no matter how else you get out of the set, it's only going to take you longer. And therefore, this must be the right decision, because if you took something longer, because the weights are non-negative, there's no way that you could get there quickly. If the weights are negative, this argument breaks down. Okay, so I'll just write this down over here. I mean, I will say, like, if you read the proof of Dijkstra's algorithm from CLRS, it's very confusingly written, in my opinion. Like, but to me, the heart of it is really this picture. I mean, this picture is given there. It's there, but it's kind of wrapped in a lot of stuff. So what I'm saying here is simply that the distance of V to W V prime is less than equal to the distance to X plus the weight of X to X prime. Why is this the case? Because, excuse me, I chose V prime to be the minimum. I chose the edge that minimizes this quantity. So if this was flipped, then actually I should have chosen XX prime. And this is a very common argument in sort of these algorithms and like with graph theory. Just like, you know, you kind of prove by contradiction. You say, well, if there was a better way of doing it, then I should have made a different choice. Okay? And this must be less than the distance from X prime to V prime. This is non-negative. Right, so I can always add something on top of it and not change it, not change the inequality. And so what this is saying is the distance, so going from S to V and V prime, is at most the distance of going from S to X to X prime, and X prime to V prime, regardless of how you go from X prime to V prime. And so this is the shortest path. Right? This is the argument, okay? And so now, of course, you have an algorithmic question. How do you choose this edge? And we'll see that what Dijkstra does is it basically picks the right data structure to do it. So it's this nice combination of having this mathematical argument and then picking the right data structure. Okay, so let me write down the code for Dijkstra's algorithm. So there's a graph G, and then you have a source S. So we'll do our usual with initialize the estimate and the predecessor arrays. I'll just say S is a list with only little s. So S is like what you've discovered so far, capital S, and it starts off just being little s. It's a list, it's a set, you can maintain any data structure. Yes? G is your graph. Right? Okay. Now, the important data structure is we're going to say Q is a priority queue. By priority queue, think of a min heap. Okay, so it's a min heap with vertices and the estimate as the key. So you're going to store a priority queue with the estimate as the key. So you can obviously, you can build this priority queue. It's going to look a lot like BFS. So we'll say while the queue is non-empty, while the queue is non-empty, we're going to we'll run an extract min operation. So in the queue, remember, you just took the head of the queue. Here we're going to run an extract min. And so this is done a little differently than my picture. In my picture, I was thinking of looking at all the edges. And you'll see that what I'm going to write here is the same argument, but is done more efficiently in terms of data structures. So what it's saying is for every vertex that's outside S, you're maintaining the best way to get into the set. That's what that est is going to be. So let me write this and then. Okay, so we're going to append U to S. So we're basically saying we're going to add this to the set. Then for every edge, or for every, I'll say for every vertex, which is a neighbor of U. So we're looking at the out neighbors. So we have U, and we're looking at all of these out neighbors. The way to think of this picture, okay, let me change my notation and call this V prime. So that this is going to start making sense here. So think of, at some point, you haven't discovered V. You're going to discover V. So V is now in your set. And then for all of these edges, you're going to call relax on all of these edges. We're going to do relax of V prime. And if the distance of V prime decreases, right? So every time you call relax on this, on that edge V prime, you may have reduced, not the distance, I'm sorry, the estimate. Your estimate may have decreased, right? Because every time you call relax, maybe you get a better path. Then you call a decrease key operation. Decrease key operation in Q for that vertex V prime. Because it's a priority queue. It's a min heap. So remember, when I taught this, I did a max heap and I did an increase key operation. And here it's a min heap, so you do a decrease key operation. What this means is when the key of a node changes, then it has to kind of swim, if you remember, right? So this is like a swim operation. Okay, and that's it. This is the entire code for Dijkstra's algorithm. Let's walk over this a little bit carefully to okay, let me instead show you what happens with respect to the picture. Okay, so let's just say that at some point you found v prime. You did this minimization, and so you found v prime. So v prime is now in your set. So now you have these other edges that are going out of the set. And so you want to minimize now for all the vertices, these v double primes, the ones that are out there. And the way to do this is to call the relax operation on each of these and see the vertex for whom things have reduced. If there's some vertex out there for which its distance is reduced, then you update it in the heap. So this heap or priority queue here is really maintaining these numbers, because that's what relax does. You have to think about it, you have to go back and stare at it, but essentially what relax is doing is basically looking at this quantity. Yeah, sort of, kind of. Yes?
So code-wise, when you find a estimate that's less, then it would go to the front of the heap, right? Because of min.
Or rather, it would update its position in the heap. It would update, and then finally, you're always extracting the minimum. So if you discover this v double prime so that its distance went down, then it would move in the heap. But you'll see that whatever you extract from here is always going to be the same thing here. It's just that the proof is easier to understand from an edge-centric viewpoint, like looking at all of these edges, but the implementation is more efficient with a node-centric viewpoint. Okay? So again, maybe you don't completely see why these two pictures are the same, but hopefully you understand this picture. And the code is, again, it's not very complicated. It's like BFS. Yes?
So I'm just a little confused because I thought I learned this in discrete math, but maybe using it with another one. Is this the same as basically just saying start at S and then add any visible edges, add the lowest one, and then each round, essentially, you look at all of the available edges and you add the lowest one?
You're effectively adding the lowest one, but then instead of, you have to be careful, like how do you maintain what the lowest is? So, maybe a trivial implementation or the brute force implementation of Dijkstra would do the following. It'd say, I have S, let me go over all of these edges VV prime, and then just find the minimum. That's like brute force. What this is doing is doing it cleverly by maintaining that information in a priority queue. Right? So you could just do Dijkstra brute force. Dijkstra brute force would be every time you have S, look at all of these edges VV prime, and then compute this minimum.
This is a specific solution for computers, I guess.
This is a specific implementation of that idea, which is kind of clever because what it says is by maintaining information at the nodes, you can kind of quickly find out who the minimum is without going through all the edges. So you want to find this minimum quickly. And anytime you think, I need to find a minimum, you should think binary heap, like priority queue. That's how you kind of discover the data structure. When you're always trying to say, find the minimum of some set under some operations, think binary heap. And so what Dijkstra does is it basically, Dijkstra's algorithm uses a binary heap to extract this quickly. That's the idea. Yes? So, okay, so by maintaining all the information, what I'm saying is something like this, that, let's get rid of. So let's just say that this is your capital S at some point. And these are all those VV prime edges. Let's just say magically at some point, what you're trying to do is minimize over the edges VV prime. You're minimizing over these edges, the distance to V plus the weight of VV prime. This is the quantity you're trying to minimize, right? So you have this quantity that you're minimizing. Now what is the problem is that when you add V prime to S, you have new things to consider now. and these quantities are potentially going to change. So when you add v prime to s, so now maybe s is that. Now there are these other edges that are going out of here. And you have to consider, maybe for this vertex here, it's better to go through v prime than to go by what it was initially. So you have to consider this edge and kind of update these quantities. That update is happening over here. So the priority queue is kind of maintaining all that information. I don't know if that makes sense. Like the priority queue is really maintaining what is the best way of going from S to the outside of S. And every time S changes, it has to update all of that information. Like all of these? Yeah? You're looking for the lowest here, but maybe the next lowest was actually here. Like it could be the case that after finding this, so v prime goes into the set. Now the next lowest thing is not from v prime there, but actually it's from x to here. Right? Because the new things you've discovered may actually be further away. So you're it's kind of like, think of it as you've sorted all the things and you're just picking out the next thing in the sorted order. Except what happens is that these numbers change, because as you discover v prime, you may discover new paths to existing vertices. Like let's say from x you could get there, which you didn't see this other path before you actually put v prime in your set. And when you put v prime, then you realize, oh, this is actually shorter than going from s to x to there. So you kind of have to update the information, which is what happens over here. Again, it takes a little bit of careful thought to kind of see why is it that Dijkstra's algorithm as written here is implementing the idea that I discussed. Takes a little bit of you have to probably run Dijkstra's algorithm on an example with about 6 vertices, and then you'll kind of see how the information is evolving. But as long as you kind of understand what this code is doing, and you kind of understand that other picture, you have to go and stew over it. Okay? So let me just write down the running time of Dijkstra, because that's sort of the important thing. So this is clearly just O of n. This is just O of 1. This can be done with O of n. It's a build heap. So you can do this in O of n. The extract min runs in log n time. The appending is just O of 1. The relax operation here is also O of 1. And this operation is O of log n. I'm sorry, why is? No, it's not just finding, but removing it from the heap.
Oh, so you have to rotate.
You have to, well, not rotate, you have to do that swaps.
Right, right.
So it's extracting. So the extract max is log n. The decrease key is log n. What is the overall running time, though? Now this you have to think a little bit. Yeah? How many times is the extract max going to be called? How many times is it going to be called? Yeah?
I'm just going to go on and say if it's a particularly bad situation, then like worst case is like n or something. Right?
I mean, if you think about it, you're going to do n because every vertex is extracted at most once from the heap. Once it's extracted from the heap, it goes into S. It's actually never going to go back into the heap. So this is going to be called n times. What about this? How many times is this called in the overall procedure? How many times are you going to call a decrease key operation? You already have, yeah?
Worst case,
Worst case?
m times as well?
M or N? N. No. Yeah. It's M. For every edge, you're going to call this at most once. Because you're going to look at every edge once. When do you look at the edge? When U is, sorry, it should be V over here. Like when this exits the heap, then you look at all of these edges. So you look at all of the edges exactly once. Each time you look at the edge, you call this. Right? And this is M times once for each edge. Right? Once for each edge when V is DQ'd. By V, I mean this V over here. And so the total running time and you can argue it's in this case it's theta. It's actually M plus N log N. And if I'm assuming that M is at least N, then you get M log N. Note that Bellman Ford was M times N. It's a huge improvement, right? So it's like this linear search to binary search type improvement. M times N becomes M log N. So this is a big improvement. Okay, so what I want to do is, before we finish, I just want to quickly just summarize everything that we did today, like just the basic facts that you need to know. So single source shortest path is you fix the source S, get the shortest paths from S to all vertices V. So remember, there are these 4 things that I described. So I'm going to give you the first fact you need to know. If the G is unweighted, then you do BFS, runs in linear time. Right? This is sort of this is what you need to implement for homework 4. Okay? So the second situation is that G is weighted.